Power factor penalty. Nowadays, many of the MSME industry segment, they are paying huge amount, an appreciable fraction of their monthly electricity bills towards the power factor penalty. How this can be avoided by the MSME industry segment as well as in the building segment, especially in the residential and commercial, gated community residential and commercial segments in their common utilities. Let us look into it in deeper and how to come out of the power factor penalty, especially in the MSME segment. So, to avoid the power factor penalty, especially in the industry segment, the industry management has to depute a person, either an electrical or they can just mold the team to just record the EB. They have an excellent EB incoming digital trivector meter. They can day wise or shift wise monitor the parameters, especially the kWh and kVh, and the averaged power factor recorded till date. That is, the averaged power factor means the accumulated power factor as on date from the previous build date as such. So, if the cumulative power factor is less than 0.85, definitely you must add a plain capacitor today at many of your motor panels that are rated above 3 HP, 3-phase motors. So, ultimately the power factor will start going up in each and every motor end, and tomorrow onwards you can see the cumulative power factor will increase gradually, and day by day you can bring up your power factor to say around 0.95 to avoid the PF penalty. Even if it is above 0.9 also you can avoid the PF penalty, but only thing you have to monitor the capacitors that is put in the motor panels in your machines, either in the production or utilities, and ultimately you can improve the power factor gradually for any of your billing period as such. Why this power factor goes low, especially in running your motors in both the production and utility machines? Because EB wants you to maintain a power factor of around 0.95 lagging at the EB incoming, but all your motors, say it is around 50 to 75% loading, the power factor average you can see from a 5 HP motor to 100 HP motor here at quarter loading and half loading and 3/4 loading and full loading. The power factor is around 0.6 to 0.7 in that range only. So, when the load and compensation is definitely required for all your 3-phase motors rated above 3 HP. So, this is the easiest shortcut to improve the power factor, easiest exercise. It can be done instantly, you can see the result to retrofit the load and power factor capacitor in all your motor panels and increase the power factor gradually day by day, and ultimately you can avoid the power factor penalty. Say if this month it has come to you, from next month onwards you can avoid the power factor penalty by retrofitting this type of PF capacitors as such. This load and PF compensation capacitors, say at the rate of 1 kVR for 3 HP and for 3-phase motors, for example around for your 10 HP motors either in the production or the utility, say around 3 kVR capacitor. Likewise, the capacitor has to be sized for your 3-phase motor rating and it needs to be installed. Normally it is said the no load kVR of the given motor, 90% of the no load kVR of the given motor, the capacitor needs to be installed. In a simpler way also, normally the industries feel the no load amps, 90% of the no load amps of the given motor, that almost is equivalent to the equivalent kVR to be installed in any of their given motor panels. So, likewise retrofit in all your machine starter panel, this will increase the load and power factor above 0.9 lagging gradually as such. You can also ask your electrical man to fix the correct sized capacitor and an MCB, miniature circuit breaker, at the motor control panel to switch on and off the capacitor to check the capacitor is working or not in a T based connection, one end to the motor, the other end to the EB supply, and the other end the center connection is towards the capacitor. The MCB towards the capacitor can be switched on and off to see the amps going for the motor is going down or high based on the capacitor added retrofitted to the motor. In all the production and utility machines above 3 HP or any of the other critical machines, basically linear loads, I am talking about the linear loads, I will talk about the non-linear loads later as such, which runs for whole days, full day. This definitely we can check this power factor improvement in each and every day, each and every shift and each and every day. Ultimately, we can definitely come out of the PF penalty coming to our MSME segment as such. This is a typical case study, a 50 HP. I will suggest the industry segment, all the people who are implementing these power factor capacitors in their panels, definitely look into this case study. It is an excellent case study. It is on the 50 HP motor. Around 15 kVAr capacitor has been retrofitted for the given motor. You can see the motor without capacitor, you can see on the motor with capacitor, the percentage change in the parameters, electrical parameters, you can see it is an excellent case study, which you can yourselves do it in your industry premises just to confirm whether the power factor improvement is there in each and every motor where you have installed the PF load and PF compensating capacitor as such. So, this reduces the kilowatt and kVA and improves the overall power factor for the given motor system. So, you can see the kilowatt reduction say around 3% and kVA reduction. You can see the demanded kVA is from almost 46% it has reduced. So, the 15% 15 kVA only is the with the capacitor. It means 15 kVA capacitor is put in line, it is a 440 volt rated capacitor, and so around 13 kVA has been applied to the existing network as such, existing T connection as such, and the kVA reduction is almost 17%, and the power factor improvement is around it has come to around 0.92, and 15% improvement in the power factor is there. So, this is what each and every one of the MSME segment needs to put in your motors which are not having any VFD or any drives in your motor or your motor panel. Normal motors, 3-phase motors above 3 HP, this exercise needs to be done. Instantly you can see the result, and definitely you can improve the power factor in your premises, and you do not need to pay the power factor penalty hereafter as such. So, summarizing of putting the capacitors in your electrical distribution, if it is only a few motors and individual capacitors will do, and the motors are steadily working and steadily loaded. So, and many motors are there, you can put a fixed capacitor bank at the SSB level. This is also very much economical. The automatic power factor control bank, it definitely comes in when there is a varying stages of loading for your given motors. When your motors are loaded say from 30% to 80% or 90%, the variation of loading is there, then the automatic power factor control APFC needs to be retrofitted in the EB incoming side to maintain a power factor of say around 0.95 lagging always throughout the billing period as such. So, the combination of individual capacitors at the motor ends and the fixed bank at the SSB, for some of the motors smaller HP motors, we would not have installed the load and PF capacitor because it is meant for 3 HP motors and above only. So, all the SSB individual capacitors and SSB fixed bank and the APFC, this combination will be very much good to maintain the power factor of around 0.95 at your EB incoming, and this is how you need to avoid the power factor penalty hereafter as such. Here I am talking about only the linear loads where the VFD drives are not there in your system, but many of the MSME segment, because it is all market driven segment. So, you are having a VFD to know different types of output is there. Today it is around 50% output is there, the deliverable output is there, and tomorrow it may be 70% or 80%. So, the VFD plays on the production machine or in the utility machine to maintain the electrical flow parameters to deliver the output what is required for each and every system as such. If you have a machine with a VFD drive, please discuss with your machine OEM. This till now I just discussed about the normal machines MSME have which does not have a VFD, Now I am just discussing about the machines. Many of the MSME, they have VFD or many of the drives in their system. Though it is a small or medium scale industry, drives are already there in your system. The OEMs have given this. So please discuss with your machine OEM. They have already provided a DC link choke in all their VFDs, but that is not enough. That will only reduce to the minimum only the harmonics, as well as the power factor also will be low only. So let us discuss with the existing OEM who has supplied the machine OEM to provide AC line reactance choke at your VFD incoming location, and this will reduce the harmonics. Whatever we talk about the power factor improvement in a linear mode, linear motors system in the MSME segment, the same thing applies to all the VFD drives in the MSME segment. Here the harmonics need to be reduced. Maybe it is a LT service or a ST service. Harmonics reduction is very much required because the harmonics needs to be house arrested within the system. Otherwise, when it gets scattered or when it is thrown back to the incoming, this will create lot of unstable voltages and lot of electronic relay other breakdowns or interlock failures also can happen. So to avoid this VFD whatever you have installed in your production machine or in your utility machine, this needs a line reactance choke. The harmonic currents to partially arrest at the VFD incoming, you can see a line reactance choke installed in a VFD of the given system. Almost the current has come down, harmonic H5 amps, the H5 component of the amperes has come down from 65 to 28%. If you can see the typical AC reactor with a DC link choke, both are needed for the given system, because DC link choke is already given by your OEM, but you have to optionally add the AC line reactance choke, AC reactor choke. This will definitely reduce your harmonic order, reduce your harmonic percentage, say from by 1/3 it will reduce in your content as such, and this will reduce the overall capacitor bank sizes also in your powerhouse. Let us say all the MSME segment need not be LT service, you are also having a HT, you are a HT consumer, let us say, and you need to install a secondary power factor compensating capacitor at the ACP of your ME panel at your powerhouse. Apart from the load and power factor compensation, see, the load and power factor compensation is done at the field end, but at your EB room, at your powerhouse, your transformer also it's a mega inductance, thus that also needs a secondary power factor compensating capacitor at the ACP. So if your industry is, let us say, batch operated, it is working for 2 shifts only, 2 shifts a day only, it is mandatory to fix this above transformer secondary capacitor before the ACP, because all the loads are switched off, but the transformer will be running at around 0.2 or 0.3 power factor only. That needs to be improved, and it will be sensed at the EB end at the ST side. You can see once the power factor capacitor is installed, this will try to maintain the power factor above 0.8 or 0.9 lagging at the EB incoming level. If your industry has lot of non-linear loads, it is prudent to fix a reactor coupled capacitor at the ACP at the incoming location to maintain the power factor. At the same time, the harmonics also is maintained, sustained there itself, and you can see the harmonics is not amplified by installing these reactor coupled capacitors at the powerhouse, especially at the ACP end as such. When this here your transformer is always 24/7 on, and even at zero load also. For that reduction in lower running PF of the transformer, this standby compensating capacitor needs to be installed, either a capacitor, plain capacitor on a linear loaded industry, or for a non-linear load industry, reactor coupled capacitor needs to be installed. Let us try to categorize your SSBs at the field level, whether it is linear or non-linear. For linear loads, either at the machine panel at the SSB, at the machine panel means what are the contactors or the cables going to the motor end, at that point the capacitor is retrofitted at that point. And at the motor control panel, the plain capacitors are fixed. For the non-linear loads, discuss with your machine OEM and the power quality experts. They will definitely throw an excellent light how this can be optimized and reduce the harmonics as well as improve the power factor and still avoid the power factor penalty and as well as the harmonics penalty, which will come in many of the states in India. They are started, if they started putting any harmonic penalty, that can be avoided as such. This is a prevention. Instead of getting the harmonics and paying for the penalty or paying for the PF penalty, these are all the preventive steps to improve the power factor and reduce the harmonics at the incoming or the EB incoming side of our premises. If your SSB is having both a mixture of non-linear loads, let us say linear loads, some 10 motors are there with linear mode and 4 motors are there with VFD. For all the 10 motors, you install the plain capacitors at the motor control panel at the outgoing contactor end for these plain motors. And for the VFD driven motors, you have to install a AC line reactance choke at the incoming of the VFD for those 4 VFD driven motors. This is how you have to categorize, you have to clarify and make the electrical network both on the linear side as well as on the non-linear side smooth flowing of amps, at the same time improve the power factor, and by improving the power factor at the SSB or at the motor end, definitely the voltage drop from the EB incoming or from the powerhouse to your machine end, the voltage drop also gets reduced. This is an added advantage for you. Some places you can see at 410 volts you will be seeing at your EB incoming side, that is say let us say around 100 or 150 feet away, and at the machine end you will find it is only 400 or 395, 398 volts only. So this 12 volt or 10 volt voltage drop can be reduced to say 5 volt by installing the power factor load and power factor capacitor at the motor end as such. Power factor compensation by plain capacitors and reactor coupled capacitors in the first phase. Anywhere detuned capacitor banks is becoming mandatory now. When your loads are very much non-linear and they are having more of harmonics, especially in the harmonic rich industries, detuning of the capacitor bank is not an optional, but it is becoming mandatory now, especially at the SSB. And for dynamically fluctuating load, active harmonic filter may be needed, but that is the last resort to be tried depending on the load pattern, the load variation pattern. But the detuned capacitor bank at the SSB will definitely improve the power factor at the EB incoming side and sustain or maintain the harmonics at the VFD end and at the SSB end only. This will not, this is like a partial house arresting of the harmonics at the field end by these two exercises as such. In general, thanks to a lot of harmonics norms and standards, IEEE 519 dated 2014, dated 2019 and the latest at 2022, I am just trying to give a generic picture of for the given steady load, for the varying loads or a dynamically varying loads. If the harmonics is not there for a given steady load, a plain power factor capacitor up to 85 or 90% of the no load magnetizing KVR will definitely be sufficient. And if the loads are varying from say 30 to 80% for the given, when you are running the industry, your loading pattern, production pattern calls for almost 30 to 80% of loading of your motors, or variation is there in your production lines, kilowatt variation is there. APFC system to be either 100% or 70% to be made as APFC system at the EB incoming to maintain a power factor of say around 0.95 lagging at the EB incoming. If the THD has come already due to the addition of nonlinear loads in your industry segment, say around 10 to 20%, definitely the fixed detuned harmonic suppression filters and the PF correction is needed for the steady loads. Many of the industries are running at steady loads, say for like the textile mills and all, they are having more of steady loads. But some of the engineering industries like RF induction hardening or any of the automobile industries where the fluctuation of load is very severe and very narrow and very fast, dynamically varying, there you need to go for a variable detuned harmonic suppression, and in the higher case dynamically varying loads in the industry, it calls for active harmonic filter. If the THD is above 20%, see, these are all the in generic approach to the power factor improvement as well as the harmonic reduction for your given MSME segment. These are all the norms in general, and you have to discuss with the power factor, power quality experts, and also with the machine OEMs to optimize your power factor at the EB incoming at just lagging PF 0.95 and reduce the harmonics to the maximum possible. Let us say if the THD is above 20% in major odd harmonics are there, the fixed tuned harmonic filters and variable tuned harmonic filters and APFC and active harmonic filters. These are all the areas, these are all the retrofits need to be done. This is everything is based on your loading only. If the loading is steady, you can be happy with the existing plain capacitors or fixed detuned capacitors or fixed tuned harmonic filters or fixed triplen harmonic filters also, if it is a third harmonic or the 11th harmonic and all. Say if THD is 20% and above and the major third harmonics, triplen harmonic filter also, and with PF correction can be done. Depending on the loads only, either it is a steady load or a varying load or a dynamically varying load, the power factor compensation as well as the harmonic mitigation needs to be employed, needs to be deployed in your premises, and accordingly this has to be achieved. So that not alone we are avoiding the PF penalty, and we are also avoiding the harmonic penalty. It may be there, it may not come, but still the PF improvement and harmonic reduction at the EB incoming side will surely improve the health of electrical health of your industry, and you can avoid a lot of electrical and electronic microprocessor based or any of the electronic sophisticated electronic equipments or circuits breakdowns can be avoided if these are maintained in a healthy level at a optimum percentage. Thanks for giving this opportunity. All these case studies on this power factor, all the motor energy savings, all the equipment energy savings, either on the production machines or on the utility machines like motors or pumps or compressors, or all the aspects has been discussed in these books, and you can find the link to buy the books, as well as all the articles are available in my LinkedIn postings. You can go through it and implement this power factor improvement exercises in your system immediately, and harmonic reduction also if you have a nonlinear loads, and after you have implemented, you kindly share with others for the benefit of others, and it is for the betterment of the nation. Thank you. Thank you.